Welcome back everyone as we continue our exploration of surface integrals of scalar functions. In this video we're going to talk about surfaces that can be represented as functions of two variables. These are the same surfaces that we talked about at the very beginning, the first video for section 16.5. So imagine that I have some surface that can be represented as a function of x and y. So I just set z equal to some function of x and y. So an example would be this cone, the square root of x squared plus y squared. Then I can use x and y as my parameters. I don't need to parameterize the surface. And the surface integral of a function over that surface, for the function itself, I need to go from 3 variables down to 2. So I just keep x and y the same. And for z, I plug in the equation for that surface. This gives me the function just defined on that surface. And then for d sigma, we get exactly what we got when we talked about surface area of these kinds of functions. So it's the partial derivatives of that function squared and added together plus 1, and then take the square root of the whole thing. Here, d is some region in the xy plane, and we're integrating over x and y, so dA is just dx dy. We can generalize this to surfaces that can be represented as a function of y and z. So if I can represent my surface as x equals some function of y and z, then now I plug in that surface for x, y and z stay the same. The square root of, now I take the partial derivatives of this function, square them out together plus 1, and d is now a region in the yz plane, and dA is just dy dz. And similarly, if I can represent the surface as a function of x and z, y equals a function representing the surface, then I can just substitute that equation in for y, leave x and z the same. I get this similar surface area element. Now d is a region in the xz plane, and so when I integrate dA is just dx dz. So what this is saying is that if you're given a surface where you can solve for one of the variables, you don't have to take a cross product. You can just use one of these things. We saw in the last section as well that if you do parameterize your surface and you do compute the magnitude of the cross products of the first derivatives, that these agree with what you end up getting. So if you don't want to bother learning these formulas, you can always parameterize and do what we did in the last video. And that works exactly the same. The advantage here is it just saves you a little bit of work if you can recognize that your surface is in one of these cases and you just set up the integral this way without having to do the cross product. Alright, let's take a look at an example. So evaluate the surface integral of y squared plus 2yz, where the surface is a portion of the plane 2x plus y plus 2z equals 6 in the first quadrant. And so now we have the surface. It'd be very easy to solve for any one of those variables. We could solve for x, we could solve for y, we could solve for z. So I can make this problem fit into any one of these formats. So let's take a look and try to figure out which variable do I want to solve for. Is there a better choice? Well, I know, no matter which one of these I pick, that 2 variables in my function are going to stay the same, and the third variable needs to be substituted by the equation for the plane. So for instance, if I solve this equation for y, which doesn't involve dividing by 2, I could just subtract and say y equals 6 minus 2x minus 2z. I would then have to plug that equation in here and square it, and plug it in here and multiply by 2z. If I solve for z, that's still easy. Just subtract these two terms and divide by 2. I would then have to plug that equation in here into my function. If I solve for x, I leave y and z the same. My function doesn't change in this case because there are no x's up here. So it looks like this is the best case. It's going to be the easiest representation of my function because my function doesn't change at all because there are no x's in this function. I still need to compute the surface area element, but we'll get to that. So what I just said is summarized here. I've drawn the surface. Here's that plane. And we've decided that since there are no x's in the function I'm integrating, let's solve the equation for x. So say x equals the equation for the plane, and set up our integral using this second format. So as we continue to do that, here I've solved the equation for x, so this is going to be my hyz. So the plane is 3 minus z minus 1 half y. I need to integrate over a region in the yz plane, and that's just going to be the projection of this surface into the yz plane. So it's going to be this triangle, which I've redrawn here. So here's another example of the difference between S and D. S is this entire plane. But D is the region I'm integrating over, and it's just this triangle in the YZ plane. So using this triangle, I come up with bounds of integration, and here I've decided to integrate with respect to Z first, but you could also integrate with respect to Y first. There's no clear preference here. And if I integrate with respect to Z first, I'm going from Z equals 0 to this line, which is Z equals 3 minus 1/2 Y, and then in Y, I'm going from 0 to 6. So I get my bounds of integration. Next, I need to calculate d sigma, which is going to be the square root. So I need the partial derivatives of h. Let's just go ahead and do this. So the partial derivatives of h, the partial derivative with respect to y is -1/2, the partial derivative with respect to z is -1. So I just square those to get 1/4 and 1, add those together, plus 1, take a square root, I end up with 3/2. So my d sigma, my surface area element, is 3/2 dz dy. Next, I'm going to define my function on the surface, but that's already done. That's the reason we chose this parameterization. Remember, there were no x's in here, so normally I would have to plug this function in wherever I see an x, but there are no x's, so my function just stays exactly the same. This is the same function. Now I'm just restricting it to that surface, that plane. Now I set up my integral, and I integrate. So here I have my bounds of integration in y, in z, my function, which didn't change from what I was given in the problem, and then d sigma was 3/2 dz dy. So I'm just going to bring the 3/2 out front, integrate with respect to z, plug in my bounds. I need to be careful here, because when I plug in my bound 3 minus 1/2 y, I need to square it. So I need to either FOIL or use the distributive property, however you multiply binomials. Work everything out, simplify some things, so I'm going to skip some steps, but you can work through and verify all these steps. And after I've simplified things, then I'm left with 3/2 times the integral of 9y minus 1/4 y cubed with respect to y. I go ahead and integrate with respect to y, plug in my bounds, work it all the way out, and the answer is 243 over 2. Okay, so there's an example of where you have a simpler surface you can integrate over. We don't have to compute cross products and things like that. So it's a little bit simpler. But again, not all surfaces can be represented that way. So far for our surface integrals, and when we found surface area using integrals, we assumed that we had to have a smooth surface. This was the same thing with line integrals. We assumed we had smooth curves. But with line integrals, we also allowed for piecewise smooth curves. In other words, we could still integrate over curves that were made up of pieces that were smooth connected at a point where that curve wasn't differentiable at a point. So think of a triangle, right? That's 3 line segments. That's a piecewise smooth curve. We're going to do the same here and say instead of just integrating over smooth surfaces, we can integrate over piecewise smooth surfaces. We just integrate over each smooth piece and then add the integrals together. Now for curves, the places where the curve was non-smooth was allowed to be a point. For surfaces, the places that are non-smooth are allowed to be curves. So you just basically go down 1 dimension less. So let's do an example of this, and I'll go through it somewhat quickly since we've done a couple of surface integrals already. So I want to integrate z over this surface, and it's given by this graph. It's actually made up of 3 smooth surfaces. So we can think of this surface as a solid cylinder that's been cut diagonally, and so then it's just the surface of that solid. So we want to integrate over the surface of this solid. The surface itself is not smooth. I have these boundary regions. I have this circle here and this oval here, this ellipse, where it's not smooth, but it can be broken into 3 smooth pieces. And the 3 smooth pieces of this curve are the intersection of this solid with the xy plane, which is this disk, this S1, the bottom of it. I have this lateral surface, which is kind of just going straight up from the circle. It's the side of my solid. And I have this top piece, which is an ellipse, or filled in ellipse. That's a piece of a plane. So I've already described these 3 surfaces as part of the problem. So surface 1 is just the unit disk in the xy plane, so z equals 0. Surface 2 is where x squared plus y squared equals 1, so it's fixed on that circle, and then z is allowed to go from 0, which is the xy plane, to the plane 1 minus x. And the third surface is the plane 1 minus x, defined over the unit disk. So it's this top piece. So if I want to look at the surface integral of z over this surface, I can split it into 3 surface integrals, because S itself is not smooth, but I can break it into 3 smooth pieces. And the advantage here, at least for this particular example, is since I'm integrating z, and z is 0 in the xy plane, this whole integral just becomes 0, so really I only need to evaluate these 2 integrals. I can't use any symmetry here because this surface, neither of these pieces are symmetric with respect to z. Everything is above the xy plane, or in the xy plane. Alright, so going through this, I go through the same steps. I need to parameterize these 2 surfaces. Since surface 2 is part of a cylinder, I'm just going to use cylindrical coordinates where the radius is fixed at 1, because I have x squared plus y squared equals 1. So x and y become cosine v sine v. Z I'm going to just call u. And here I have u goes from 0 to 1 minus cosine v because I have these bounds for z. In this piece of a cylinder, I'm always going from the xy plane to this plane above. So it's going from 0 to 1 minus x. Oh, and I should have mentioned before that I've the only time in this class drawn the x-axis here and the y-axis here. And the only reason I did that was because I drew this solid incorrectly and I didn't want to draw it again. So my apologies there. But just keep in mind that now this is the x-axis and this is the y-axis for the only time this semester. My apologies for any confusion. Okay, back to my parameterizations, and since I'm going all the way around, v goes from 0 to 2 pi, u is going from 0 to 1 minus cosine v. I just replace x with cosine v. Now for this plane, I could do what we did in the last example and leave x and y as parameters. And since I have a surface where z is solved for a function of 2 variables, so z just equals 1 minus x, but I'm going to end up integrating over this disk, and I'm going to want to use polar coordinates for this disk. So instead of just leaving x and y as parameters, I'm going to go ahead and switch to cylindrical coordinates again. Now I need my radius to be variable since I'm filling in the disk. So the first and second components are u cosine v, u sine v, and I replace z with 1 minus x, which is 1 minus u cosine v. U goes from 0 to 1 because it's the unit disk, and it's the entire unit disk, so v goes from 0 to 2 pi. So those are my parameterizations. Finding the surface area elements for the second surface, I take my partial derivatives. Partial derivative with respect to u, I just get 0, 0, 1. Partial derivative with respect to v, I get negative sine v, cosine v, 0. I cross them, I get negative cosine v, negative sine v, 0. You can verify this. And then this is a unit vector. So when I take the magnitude, I get 1. So d sigma 2, the surface area element for this second surface, is just du dv. For the third surface, I do the same thing. Take partial derivatives, cosine v, sine v, negative cosine v, the partial derivative with respect to v, negative u sine v, u cosine v, u sine v. I set up my cross product. It looks like it's going to be more complicated, but it ends up just being 0, 0, u, which you can verify. I take the magnitude, and I just get u. Now this should be the absolute value of u, right? If you take the square root of something squared, you should get the absolute value of u. But since I'm taking u to go from 0 to 1, it's always non-negative, so the square root of u is the same as u in this case. So my surface area element for the third surface is u du dv. Now I'm ready to define my function on the 2 surfaces, but the function I want to integrate is just z. So in order to define the function on the 2 surfaces, all I need is this third component of the parameterization. This tells me what z should be. So on the second surface, z is u. On the third surface, z is 1 minus u cosine v. And so now I'm ready to set up my integrals. The integral of z over that surface of the solid. The first surface, z is just 0, so it disappeared. On the second surface, I'm integrating u, where u goes from 1 to minus cosine v, and v goes from 0 to 2 pi. And on the second surface, I'm integrating 1 minus u cosine v times u, because that was my d sigma. And v goes from 0 to 2 pi, u goes from 0 to 1. So then here, I'm just distributing the u. I start integrating, and I'll allow you to go through these details and verify the work that I did. 2 things I want to point out, though, as you're going through. At one point, after I've integrated both of these integrals with respect to u, I end up with 2 integrals in v that are both going from 0 to 2 pi. So I just go ahead and combine them. If I'm integrating with respect to the same variable over the same interval, I can just combine those two integrals into one integral. So here, instead of two integrals with respect to v going from 0 to 2 pi, I just added them together and made one integral. And the other thing I want to point out is that here I've replaced cosine squared v with 1/2 plus 1/2 cosine 2v. So I've used that trig identity there. And then as you follow through, you should get that the answer is 5 pi over 2. The last thing I want to talk about in this video are what are some applications of scalar surface integrals. So why might we want to use these things? So the first is if you know the density of some material on a surface, so you can think of a shell or a plate or any kind of surface you like. If you know the density of some material that you care about, you compute a surface integral of the density to get the mass of that substance. From there, you can compute center of mass, moments of inertia, just like things we talked about with line integrals. And really, what are you doing with a surface integral? You're adding up some function over a surface. So if the function describes the distribution of some quantity that you care about, then what the integral does is gives you the total amount of that substance in the surface. And that's really the main application of these surface integrals. I'm sure there are some other applications out there, but that's all we're going to talk about here. And now in the next video, we'll continue surface integrals, but we'll talk about surface integrals of vector fields.